We'll look at developing a rule known as the chain rule that we can use to evaluate the derivatives of compositions of functions. So motivating the chain rule. Suppose that the rate of change of the amount of water in a pot, W per degree Celsius, is dW over dC. The change in temperature or change in amount of water per change degrees Celsius, i.e. water is boiling in a pot, let's say. Suppose that the temperature C of water is changing per hour T. So we now have a derivative for C, dC over dt. If we want to obtain the rate of change of the amount of water per hour instead of per degree Celsius, we could apply unit conversion from science. So dW over dt is going to be equal to change in water divided by change in time, which is going to equal a change in water divided by change in temperature times a change in temperature divided by change in time, or dW over dC times dC over dt. What we could say here is the dC's cancel out to leave us with the dW over dt, and from perspective of compositions of functions, we could say that W is a function dependent on C, but C itself is a function dependent on T, so we could say that W is a composition of functions. Either way, what we notice here is we take the derivative of W with respect to C and multiply it by the derivative of C with respect to T in order to get the derivative of W with respect to T. So now let's consider the function, extend this principle and idea to a function. So let's consider the function y equals 3x squared plus 1 squared. This is a composition of functions with the outer function being y equals u squared and the inner function being u equals 3 squared plus 1. Well, we should note that as we take the derivative of y with respect to u, we're going to get 2u, and if we take the derivative of u with respect to x, we're going to get 6x. To get dy over dx, let's try what we saw on the prior slide, and it'll try a little bit of unit conversion by multiplying dy over du by du over dx. This should say du over dx, not dy. So dy over dx equals dy over du times du over dx equals 2u times 6x. Again, dy over du is 2u and du over dx is 6x, which gives us 12u times x, which equals, when we substitute u back in, 12x times 3x squared plus 1, or 36x cubed plus 12. So let's make sure that this is correct. If we expand y right here originally, we're going to get y equals 9x to the fourth plus 6x squared plus 1. And we're going to get the subsequent derivative is 36x cubed plus 12x. We see that our method works here. So what is this method? This method is known as the chain rule. It states that if y is a composition of functions, f of g of x, then the derivative of y with respect to x is going to equal the derivative of f with respect to g times the derivative of g with respect to x. Or if we want to call g u, df over du times du over dx. That is, the derivative of f with respect to x is equal to the derivative of f with respect to g times the derivative of g with respect to x. Just saying that again to hammer home the point. In terms of Lagrange notation, the chain rule states, states that the derivative of y prime equals f prime of g times g prime of x, right here. So this one is worth writing down because this is useful for arbitrary functions, as we'll see in class tomorrow, and also at the end of this section a little bit too. So to work with the chain rule of a function f, you can follow the steps below. Identify the inner function g, or u, whichever you prefer to call it. Take the derivative of the outer with respect to the inner, df over dg. Take the derivative of the inner function with respect to x, dg over dx, and multiply df over dg by dg over dx to obtain your derivative. So example 1, what is the derivative of f of x equals tangent of x cubed plus 5x? Again, derivatives are like onions because we're working with layers here. So the first thing that we're going to do is identify our inner function. It's u equals x cubed plus 5x. So df over du is going to equal the derivative of tangent of u, which is going to be secant squared of u. Now the derivative of u with respect to x is going to be the derivative of x cubed plus 5x, which is going to be 3x squared plus 5. Taking the results and multiplying the results, we're going to get secant squared of u times 3x squared plus 5 equals 3x squared plus 5 times secant squared of x cubed plus 5x when we substitute u back in, thus saving us a bunch of time. And in fact, we'll actually look at how to condense this down even further in class when we get more practice with it, but right now we're going to highlight steps in order to do this. So if we want to apply the chain rule multiple times, let's say to a more complex example, the idea is still the same. We work our way from the outside in. Okay? So let's say we're looking at the function y equals cosine squared of e to the negative 2x. Ooh, that looks difficult to evaluate. So, but what we do is we work from our outside in. So what we can see is that our outermost function is going to be u squared, where u is equal to cosine. Okay, so now if we focus on the cosine function, u equals cosine, it's not going to be u equals cosine of x. We have another inner function, v, what we'll call it, v equals e to negative 2x. So our next inner function is v equals e to the w, but now we got to keep working our way in because w itself is not x. W itself is negative 2x. So our last inner function is going to be negative 2x. It's like Inception. You got to keep working your way inwards, just like the movie Inception a little bit. So again, we identified that u equals cosine, or our outermost function is y equals u squared for u equals cosine of v. Our next step, v, is e to w, and then our last step is w equals negative 2x. So now what we're going to do is we take the derivative of each part with respect to the variable. So y equals u squared, we take the derivative of that, gives us 2u. U equals cosine of v, we take the derivative of that with respect to v, gives us negative sine of v. And then the derivative of v with respect to w is e to the w. And then lastly, the derivative of w with respect to x is equal negative 2. This is a very complicated example here, obviously, but it's meant to show how we can apply the chain rule over and over and over again. And we'll get more practice with this in class. Okay? So don't worry if you're still looking at this and still a little bit unsure. So dy over dx is then going to be dy over du times du over dv times dv over dw times dw over dx, hence why we call it a chain. The du's cancel out, the dv's cancel out, and dw's cancel out. So our result is we're going to get 2u times negative sine of v times e to w times negative 2. So now what we're going to start doing is we're going to start substituting things back in. First, we're going to substitute u equals cosine of v. Okay, we're going to work our way from the outside in. So that gives us 4 times cosine, 4 times cosine times sine times e to w. And then we're going to substitute v equals e to w in, leaving us with e to w inside now. And then lastly, we substitute negative 2x in to get our derivative. 4 times cosine e to negative 2x, sine times e negative 2x times e to negative 2x. Again, this is a little bit complicated example. We'll spend more time with this example in class because the repetitive chain rule is a little bit more complicated than just the single-use chain rule. So now we're going to apply the chain rule to see how we can determine the derivative of an inverse function. So recall that a function g is the inverse of a function f if g of f of x equals x and f of g of x equals x. So we're going to focus on this first expression right here, and we're going to take the derivative of g with respect to x by applying the chain rule. So the derivative of g with respect to x, again recalling the Lagrange notation for a chain rule, is going to be g prime of f times f prime of x. The derivative of g with respect to our inner function f times the derivative of f with respect to x. And then on the right-hand side, we're going to have the derivative of x, which is just going to be equal to 1. So if we focus on a specific point, x equals a, f of a equals b, so in this case, x equals a refers to the original function, f, one is going to obtain that g prime of b times f prime of a equals 1 by substitution. Solving for g prime of g prime of b gives the derivative of an inverse at a specific point. The derivative of our inverse, replacing g with the notation f inverse. The derivative of the inverse at a point x equals a, f of a equals b, is going to be equal to the reciprocal of the derivative of your original function at the point x equals a. So that's all you need to do is take the derivative at x equals a and the reciprocal of it to get your derivative, your inverse at that specific point. So one big implication of this is it can be used to determine the existence of an inverse at a point, what's known as the inverse function theorem. If a function f has a horizontal tangent line at x equals a, i.e. the derivative of f at a equals 0, then the function is not invertible at that point because we're going to have 1 divided by 0. And that's all there is to this slide right here. It's just a nice little extension of what we saw on the last slide. So in order to calculate the derivative of inverses, okay, recall that the point xy equals ab for f actually corresponds to the point xy equals ba for f inverse. So steps to follow to determine f inverse of b, okay, is that you're going to solve for b equals f of x to determine the corresponding x coordinate x equals a for f of x. So oftentimes these problems will give you b for your inverse, okay, the value for your inverse that you're interested in, but it won't give you the corresponding x value for your original function. So what you have to do is recognizing that b for your inverse is equal to the y value of your original function, you have to set b equal to f of x to determine the corresponding x coordinate for f of x. Next, you're going to determine the derivative of f and evaluate it at x equals a. And then you're going to take the reciprocal of your derivative at x equals a to determine the derivative of your inverse. So again, the big thing to watch out for, and we'll see this in the next example, is that when they ask you for a derivative of an inverse at a specific point, that refers to the point for your inverse, which the x coordinate for your inverse, which refers to the y coordinate of your original function. So you have to solve for b equals f of x to determine the x coordinate for your original function. So in terms of example, this is how a standard problem would look. Let g equal the inverse of f, be the inverse of the function f of x equals x cubed plus 1. It asks us to determine g prime of 9. So again, 9 here won't refer to x for our original function, it will refer to x for our inverse function. So first we need to determine the x coordinate of our original function, x cubed plus 1. So we set 9 equal x cubed plus 1 to solve, and we're going to solve that equation to get x equals 2. That's a tricky, difficult part. Now after this, all you have to do is take the derivative of f at x equals 2, 3x squared, plug 2 in, which gives you that f prime of 2 is equal to 12. And then you take the reciprocal to get g prime of 9. And that's all you have to do to determine your inverse.